to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be looking at Unit 10, Lesson number 5, on the Polar Curves Day 1, the Limacons. So there's a great history of people studying all sorts of different curves in polar form. It's always kind of questionable what we should study, what we shouldn't study, how much we should really dig into it. We've already seen polar equations of simple things like lines, which weren't so simple, circles centered at the origin, etc. What we're going to be doing is spending 2 lessons looking at some of the classic curves and trying to understand why they behave the way they behave. This is an exceptionally rich topic that can be approached in many, many different ways. In these lessons, we're really exploring and also trying to understand. So, treat them as you will. Let's take a look. Polar curves can just be amazing, really amazing. And what's really kind of cool about them is that they can model things that otherwise really couldn't be modeled easily with Cartesian equations. For instance, these 2 spirals would have, to put it mildly, kind of beastly equations in Cartesian form, but in polar form, they're not too bad at all. In fact, a spiral is quite easy to create in polar form. Plus, let's face the facts, that's kind of cool looking, right? So we're going to be trying to understand this a little bit today. All right, the limacon, from the French word for snail. Whether limacons look like snails or not, that's going to be for you to decide. All right, all limacons have a relatively simple formula. They always look like r equals some kind of number. Let me just throw one out there, like 5, plus some other number, let's say 2, times cosine theta. You could also easily have a sign there instead of a cosine. You could have -3 plus 7 times sine theta. Most often these coefficients are positive, so I don't know why I even put a negative there. They could be negative, but it just makes it a little bit more difficult to think about it because it makes it hard to think about negative radii. Both of these 2 would be considered limacons. Okay? So what we're going to do obviously today is really think about how the value of A and the value of B then affects the way that these limacons end up graphing. Okay? Let's go on to the first problem. All right, it says consider the limacon whose equation is r equals 1 plus cosine theta. This is one of the simplest limacons. The A value is 1, the B value is 1. First things first, let's fill in the table below. In fact, what I'd like you to do is fill in the table, pause the video, shouldn't take you more than about a minute, and fill in those values. All right, let's do it. Well, if I put my 0 in here, the cosine of 0 is 1, 1 plus 1 is 2. If I put pi over 2 in there, the cosine of pi over 2 is 0, so r is 1. If I put pi in there, the cosine of pi is -1 plus 1 is 0. If I put 3 pi over 2 in there, the cosine of 3 pi over 2 is 0, so my final answer is 1. If I put 2 pi in there, the cosine of 2 pi is 1, 1 plus 1 is 2. Now letter B is a little bit weird. It says sketch a graph of r versus theta. Notice this is not x versus y. This is r on the y-axis, theta on the x-axis. Then it says based on the graph, what can you say regarding the positive, negative nature of r? So here is where we're going to rely on our ability to sketch trig graphs, although I suppose we don't even need to do that. We've got like a table of values, right? We got it right up there above. So I'm going to put these on. Right, what do I have? I have 0, 1, and 2. I know that at 0 I'm at 2, at pi over 2 I'm at 1, at pi I'm at 0, at 3 pi over 2 I'm back to 1, and at 2 pi I'm at 2. So I have a really poorly drawn trig graph, kind of looking something like that. Right, we know this, right? We know it's got a midline or an average value of 1, an amplitude of 1, makes all the sense in the world, right? That was supposed to be my midline, but I kind of missed. So what we can say is that there are no negative r values. There is one r value of 0, right? And I'm getting the feeling that's going to be important, right? We talked about this in the last lesson, what it would mean for r to be 0, where you would be in the coordinate plane. but we'll get to that, okay? So I'm going to clear out this text, write down what you need to. Here we go. All right, continuing on in this problem. I'm going to throw this graph back up there really quick. Something like this. Remember, this was at pi. This was at 2. This was at 2 pi. These two aren't as big of a deal, the 3 pi over 2 and pi over 2. Sketch a graph of the polar curve in the Cartesian plane, verifying your calculator. This type of Limason is known as a blah, blah, blah. We'll get there. So now, remember, what I want you to be thinking about is taking this x-axis, but it's really the r-axis, and now rotating it, right? So what I know is that I know that I'm going to be a radius of 2 when my theta is 0. But then my radius decreases, and by the time I'm pointing upwards, right, I'm at an angle of pi over 2, my radius is now equal to 1, right? So my radius is going to decrease that entire time. Now, it continues to stay positive, so let's say I was at 3 pi over 4, something like this, right? So my angle is out this way. My radius is still positive, but it's getting smaller, right? So that thing is decreased. And in fact, it's going to continue to decrease until I hit pi when I'm back at the origin. Now, what's kind of cool is then, as the angle continues to rotate, right? Think about that polar graph paper. Now, my radius is going to get bigger again. And in fact, by the time the angle gets down to 3 pi over 2, my radius is going to be back to 1. Remember, that's, oh, here I've got my axis pointed down at 3 pi over 2, and I go 1 unit out. By the time I've rotated all the way around to 2 pi, I'm all the way back there. All right. It says verify this on your calculator, so I would ask that you do that. I don't want to take the time to open up the TI-84. We've done plenty of polar calculating, or sorry, plenty of polar graphs. This particular type of Limason is known as a cardioid. No great surprise, it kind of looks like a heart. And this sharp point, and it truly is a sharp point, if you were to zoom in, what you would see is you'd see something like that, very, very sharp point right there where the radius goes to 0. This thing is known as a cusp in mathematics, very sharp point. It's kind of like a very, very special corner, if you will. All right, so that's a cardioid, which is a special type of a Limason. And that happened when the A and the B values were the same. So I'm going to delete this. Okay, it's gone. And let's continue to play around with things. Now, letter B, number 2 says, given a Limason whose equation is r equals b plus cosine theta, sketch a graph using your calculator of the Limason obtained for the following values of b. So in other words, what we're going to do is we're going to look at a situation where this number is greater than the coefficient on cosine and one where this number is less than the coefficient on cosine. Because it's really not about what A and B are. It's about whether one of them is bigger than the other. Okay? So what I'd like you to do is pause the video right now, use your graphing calculator to sketch graphs in both A and B. All right? And then we'll talk about some special features that you see. All right, let's go through it. Extra long pause because you had to do 2 of these graphs. So, depending on what window you used, in this situation, you get something that looks a lot like the Limason, but with one pretty crucial difference. The Limason at this point kind of nosedived into the origin. This one doesn't do that. You don't get any kind of sharp corner or anything like that. In fact, if you zoomed in on this area, you'd see a nice sort of smooth transition, something that looks like that. This thing, I love this, is called a dimple. It's called a dimple. On the other hand, when you graph this one, right, what you end up getting is something much cooler. Here it looks like you're going to get a cusp. but instead you get something that looks like this. This is what's known as an inner loop. All right. So then the real question, exercise 3, why is this happening, right? Why does the Limason in B, right, have an inner loop, but the one in A doesn't? And maybe even, why is it that in exercise A, you're getting this dimple, but way back in problem number 1, you got that cusp, right? Because right now we've seen 3 things. We've seen a cusp, we've seen a dimple, we've seen an inner loop, right? So why is that? Pause the video now and take a really good thought, or a really good amount of time to think about it. All right, let's do it. Well, it's really about whether or not R can go negative. So can R go negative? Right, that's what it's really about. If the answer is yes, then what you're going to get is you're going to get that inner loop. All right. So in other words, when we look at something like this, 0.5 plus cosine theta, right? Eventually cosine theta is going to hit a value of -1. And when we add the -1 to the 0.5, we're going to get a negative radius. That's what gives us that inner loop. Can R go to 0? If R can go to 0, but it can't go negative, not negative, right? That was our first situation, right? That was when we had R equals 1 plus cosine theta, right? The smallest this can be is -1, so that the R can go to 0. That's when the R comes crashing into 0, into the origin, and then comes out of it like that. That's when we get that cusp. Right? That's when we get the cusp. On the other hand, if R stays positive the entire time, then the best that can happen, right, the best that can happen, and this is the situation where we have R equals 1.5 plus cosine theta, is that cosine theta can, if you will, sort of eat into the 1.5, but it can't erase it entirely, and it certainly can't make it go negative. In fact, the smallest that the radius could have ever been in that case was a half, right? So it's kind of cool. When the R goes negative, the curve will literally, if you will, kind of loop back on itself, right? It'll get that inner loop. When R goes to 0, we'll just get this sharp cusp. And when R has to stay positive, sometimes we'll get a dimple. I wish I could say always, but that's going to be part of homework, okay? So I'm going to delete the text. Okay. And we're going to have a little problem to test whether or not you understood that. So exercise 4, it says describe whether each of the following Limacons would have a dimple, which is highlighted for some reason, a cusp, or an inner loop. Verify your answers by inspecting a polar graph on your calculator. Now when you do that, you very well may have to play around with the radius. For instance, you may very well have to play around with the window, not with the radius. But for instance, like if I were to look at this, right, the largest that my radius could possibly be would be 15. But that means that I should really use that to set x min. I don't know where I got 15 there. I meant to say 12. You might want to set your x min and your x max to be -12, 12, y min, y max, -12, 12, etc. But what I'd like you to do is I'd like you to pause the video now, and I would like you to think about whether each one of these has a dimple, a cusp, or an inner loop. Okay? All right. This is actually pretty easy. In this situation, the R can certainly go negative, right? In fact, it can get as small as -2. And because of that, this thing is going to have an inner loop, easily verified on the calculator. Here, R min, the smallest that could ever be is 0, right? Because the smallest this could be is -1, and then you have 3 minus 3, etc. So what this thing is going to have is a cusp. It's going to like that, right? On the other hand, here, the smallest that R min could possibly be is 2, right? If I have that's -1, that would be -8, that would be 10 minus 8, or 2. So this thing is just going to have a dimple. You won't always get a dimple in this case, and on the homework you'll play around to see if you can figure out what a stronger criteria is to know whether you have a dimple. But certainly you're not going to have a dimple in either one of these cases. Okay? Each one of these can be pretty easily verified on your calculator, pretty easily, although you might have to do some zooming. All right, I'm going to clear that out. Let's take a look at the last problem. Exercise 5. Without using your calculator, sketch a graph of the Limason r equals 4 plus 4 sine theta. Now, one of the things that's a little bit tricky here is that we have a sine here, not cosine. All right. So that means that our maximum radius, is going to be at theta equals pi over 2, right? And in fact, our max at that is going to be 8. Right, where we're going to get our cusp, our minimum r is going to be at theta equals 3 pi over 2, and our min is going to be 0, right? So that's going to tell me that I have a cusp. You could even figure out your beginning radius, right? If I put a theta of 0 in, I'd be at an r of 1, 2, 3, 4. But then I'll be at 1, 2, 3, 4, 5, 6, 7, 8. But then I'll be back to 1, 2, 3, 4. So that's a pretty boring curve. But then what happens is we get something like that. Not perfect, but you can certainly verify on your calculator that it's more or less correct. Whew. All right, those are Limasons. I'm going to clear out the text. Again, the bigger picture isn't the Limason. The bigger picture is how r as a function of theta can do interesting and yet predictable things based on whether it's positive, negative, or 0. Okay? All right, so that was our first day on polar curves, the Limasons, little French for you. Next time we're going to be looking at what are called polar roses. But for now, let me remind you that this has been an Arlington High School Math 4 Honors lesson. I'm Kurt Weiler, and until next time, keep thinking.